Hello world, my name is Victor Engelmann and I'm not a huge fan of encryption. Mainly because the developers of cryptographic software seem to be allergic to any kind of comprehensible user interface. I mean, the two main principles of UI design are you have to think from the user's perspective and you are not the user. And the developers of cryptographic software don't seem to follow these rules in any way. I mean, when you look at cryptographic software, it often looks like it was designed only for people who have studied cryptography, right? And when you look online for help, most videos and web pages are either way too shallow, like they give you really only a very rough idea of what asymmetric encryption is, for example, with videos that are like 3 minutes long or so. And others go into the topic way too deep and are way too complicated. And that's why I'm making this video now. Okay, so let's start. Let's say we have two people who want to communicate with each other in some way. In literature, they are called Alice because of the A and Bob because of the B. Okay, Alice and Bob want to communicate with each other. And the problem now is that between these two, there is an unencrypted network, okay, like the internet, for example. So there are some systems in between. So the data that goes from Alice to Bob passes through some other systems, and these other systems might read the packets, right? So if you did something like online banking, that would be really risky. And even if they had a direct line between them, maybe someone goes to that line and cuts it in half and puts some device in between to listen on the data that's going through the wires, okay? That would also be possible. Now, to solve this problem, Alice and Bob need to encrypt their data so that nobody in between can read it, right? And this is a problem. How do you encrypt your data? I mean, let's say you pick some password, let's say 1, 2, 3, 4, 5, and then you want to encrypt your message. Let's say the message hello, world, exclamation point. Well, then one way to encrypt this would be to add 1 to the H, 2 to the E, 3 to the L, and so on. And then you would have an encrypted text, which you could send to Bob, and then Bob would have to subtract 1 from the I to get back to the H. But the problem here is that to do that, Bob needs to have the same password. Okay, so this is called symmetric encryption, because to decrypt the encrypted text, you need the same password that was used to encrypt it. And then you are back to square one, because now Alice has to tell Bob about her password. And how does she do that? If she just sends it to Bob, then the password again goes through this unencrypted network in between, and some attacker in between could just read the password and use it later, right? So, in practice, this symmetric encryption is just not good enough. I mean, you wouldn't want to pick up the phone every time you try to go to some website and call their administrators and tell them, hey, I want to establish a connection to you. And here, this is my password. Please store it so that we can have an encrypted connection. That would be crazy, right? That just wouldn't work on a large scale. And that's why we need asymmetric encryption. Well, Alice and Bob create two different keys, a so-called private and a public key. And the private and the public key have to be different. and you can just send the public key over to Bob. And he can use that to encrypt data that he wants to send to Alice. And that's not a problem because this public key cannot be used to decrypt the text that Bob sends. Okay, so even if someone in between captures this public key, it doesn't help them. They are still not able to decrypt the text that's going over the line. You really need the private key to decrypt this, okay? An interesting side effect of this, by the way, is the private and public key will be chosen so that they are inverse to each other. And this has an interesting side effect that Alice can also send something unencrypted to Bob and also encrypt it with the private key, not the public key. She can encrypt it with the private key and gives the result of that also to Bob. And then Bob can decrypt the encrypted text with her public key and get the same text, okay? And since Alice is the only person in the world, theoretically, who has her private key, this means that this message must have come from Alice because only she is able to generate this encrypted form of the same message, okay? That's what we call it a digital signature. Okay, by using her private key, Alice can prove that this text came from her unaltered. But there is still the problem that someone could be in between, a so-called man in the middle. Although, is that still politically correct? I mean, are we saying that women aren't smart enough to do such an attack? Or are we saying that women don't have enough criminal energy to even try? Anyways, so we have this attacker in between. And, well, Alice could send her public key, but the attacker could just keep it and send a different public key to Bob. Okay, and then Bob would encrypt his messages with the wrong public key, one for which the attacker has the private key. So the attacker could decrypt it and then use Alice's public key to encrypt it again and send it to Alice. And yeah, nobody would be able to tell that this has happened. So even with asymmetric encryption, we still have this problem that there could be an attacker in between. And I mean, there is a Diffie-Hellman key exchange, but yeah, the same thing can happen with Diffie-Hellman. So that also doesn't solve the problem. And actually, there is absolutely nothing that Alice and Bob can do on their own to prevent this. Okay, this problem cannot be solved by only Alice and Bob. Okay, so what we need additionally is a so-called certificate authority, a CA. Now, what does a CA do? A CA also has a private key and a public key. Okay. And yeah, today operating systems come with copies of the public keys of several CAs pre-installed. Okay, so both Alice and Bob have a public key of the CA. Okay, they just have that. And what they can now do is, because they have the public key, they can establish a connection to the CA. I don't know, let's say Swiss sign, VeriSign, whatever. Let's encrypt. So they have these public keys, and now they can send their own public keys to the CA. Okay, and the CA can then use their private key to sign these public keys. Okay, so you then get a so-called certificate for your public key. And what Alice and Bob can now do is, well, Alice can now send her public key to Bob. Okay, so he has her public key, and she also sends her certificate. Okay, and yeah, the certificate is basically a signed version of her public key, so that Bob can then use his copy of the CA's public key to decrypt this and then see, okay, this public key here that I've gotten from Alice matches the one from the CRT, which means that this certificate must have been encrypted with the CA's private key. Okay, and if I trust this CA, which I do by default, this is pre-installed on the operating system, if I trust this CA, it means that I now trust that this is actually the public key of Alice. Okay, so nobody was in between who has switched the public key for some other public key. Okay. Okay, now let's talk about the RSA algorithm. The RSA algorithm is named after its developers, Rivers, Charmier, and Edelman. And it's actually surprisingly simple. You take the text that you want to encrypt, okay, and you just take the normal power, okay, so just the normal power to the power of some C, just the normal power function that you know from school, okay, so T times T times T times and so on times T, C times, okay, just a normal power function, okay. And after that, you take the division remainder with respect to some n. This is a very well-known operation in computer science and math. I'm not going into that. And we only have to be clever about which C and which n to pick for this, okay? We could just take some random numbers, but yeah, then probably we wouldn't be able to decrypt anything after we've encrypted it like that. The key to encrypting something in a way that we can later decrypt it lies in the Euler theorem, also called Euler-Fermat theorem, which states that t to the power of the Euler function phi of n is congruent 1 mod n, as long as t and n don't share a common divisor. And yeah, when we just add another 1 here, we get t to the phi of n plus 1 is equal to t. Okay? So this phi of n plus 1 basically wraps any t around this n module such that every text is mapped back to itself. Okay? And that's really the core idea here, because what we now do is we basically have to break this phi of n plus 1 into two parts. And one of these parts is the private key and the other part is the public key. Okay, so how do we break this phi of n plus 1 into two parts? Well, first of all, we need to have phi of n. And Euler's phi function is hard to compute in practice if you only have this n. Okay, so what we do now is we construct this n as a product of two prime numbers, p and q. And in practice, you need to take very large prime numbers so that you don't get them by doing just a few million guesses. Okay, so n is going to be p times q. And yeah, the phi function of n then is equal to p minus 1 times q minus 1. So then we have phi of n. And yeah, since we don't give anybody these prime factors p and q, nobody will be able to get this phi of n. Okay, to get this phi of n, you would have to make a prime factorization of n. We give people the n, but not phi of n. And this really is the reason why you cannot decrypt something without the private key, because if we are using really large numbers here, to get phi of n, we basically need to find these two prime factors, but yeah, prime factorization with large numbers is just hard. Okay, just takes too long and isn't worth the effort normally. And now to get a private and a public key, we basically just pick a random number. Yeah, between 1 and phi of n. This mustn't have a common divisor with phi of n. Greatest common divisor of d with phi of n must be 1. Okay. Well, actually, we can just take a prime number. I mean, we already need a prime number generator for this. And if we pick a prime number for this, then we get this GCD equals 1 for free, because D doesn't have any common divisors with any number. And now we need another number with a property that together with D, we get this property up here. Okay. And to get that, yeah, we basically need a number E such that E times D is congruent 1 modulus phi of n. Okay. Another way to write this is we need E times D minus k times phi of n equals 1. Okay, for some number k. We don't care about this k. And this is just a simple Diophantic equation. You can use the Euclidean algorithm to solve that, the extended Euclidean algorithm. And then you have this E and D, right? We have E and D. And they are basically the private and public key. Okay, so you can say E comma n is the private key, and D comma n is the public key. Or vice versa, it really doesn't matter, they are inverse to each other. So, and yeah, we can now use these to encrypt and decrypt our text here. So with T, encrypting it with the public key, we take T to the power of D mod n. That's the encrypted text. And to decrypt it now, we take the other key, so this thing to the power of E mod the same n. And this will become the original T again, because T to the D mod n to the E mod n is congruent to T to the D to the E mod n mod n, which is equal to T to the D to the E mod n. Now we have picked D and E such that this equation here holds, which means that T to the D times E mod n is equal to t to the k times phi of n plus 1 mod n which is equal to t times t to the power of k times phi of n. So we've pulled this plus 1 out, mod n, which is equal to t times t to the power of phi of n to the k mod n is equal to t times, well, we have t to the phi of n, which according to the Euler-Fermat theorem is equal to 1 to the k mod n, yeah, and 1 to the k is 1 mod n equals t mod n. Okay, so this proves that D and E are complementary to each other within this n module. But interestingly, we are doing the same operation here with the public key and the private key, right? We take something to the power of the first number modulo the second number. And yeah, this means that we are actually not even decrypting the text. We are actually encrypting it again, just with a key that happens to be inverse to the first key. The RSA algorithm is actually so simple that I recently implemented it just for fun. And I want to show you around in the code here. As you can see, it's only 159 lines, which is really not that much. So this is, I'm using 64-bit integers here. In practice, you would have some data type for bigger numbers, but the idea is the same thing. I've actually written that as a template so that you can just change out the data type that it uses. But yeah, let me show you around in the code. So here is a function that calculates a number t to the power of x modulus n. You could just multiply t with itself x times and then take modulus n. That would be quite slow though, because if x is a big number, then iterating x times would take a lot of time. So this here is a bit more clever in that the bits of x can be taken one by one, and then you only have the logarithm of x iterations of this. So in a 64-bit integer world, this means that this loop will at most run 64 times. Okay, and then yeah, applying an RSA key to some input t is really just this power modulus n, t to the power of d modulus n. And then there is a little prime number generator, but that's really trivial. It just generates random numbers, tests if they are prime, and if they are, returns them. This test for prime numbers really just tests all smaller numbers, whether they divide the number. So that would absolutely not work with bigger numbers. Yeah, then here we have an implementation of the extended Euclidean algorithm. And yeah, this here is actually the whole key generation. This would actually work for bigger numbers also. So here we generate two primes, P and Q. They mustn't be the same number, so and then they are passed to this gen key function, which, yeah, this is even the same denotation, right? We have this n as p times q, phi is p minus 1 times q minus 1. Then we generate random numbers, so e is picked as a random number, and then we apply the Euclidean algorithm to e and phi, with d as the third parameter, so that d is what we get out of the Euclidean algorithm together with the greatest common divisor. And if the greatest common divisor is not 1, then we just do it again. Okay, so because e must not have common divisors with phi. Okay, so at this point we already have d and e. D can be negative, so then we map it into the range between 0 and phi by adding a phi, and then we are already done. So here, these are the two keys that we get out of it, en and dn. Okay, then we have generated this key and can then encrypt it, decrypt it, and let's see if it works. So here's only this rsa.cpp. Okay, it has compiled. Okay, now it wants a number to encrypt here. So I'll give it 42. And 42 encrypted using this RSA key is 23,212. And decrypted using this private key, it becomes 42 again. So yeah, 42 was the original input, and it's also the output. So this encryption and decryption has worked. Okay, so much for the theory. Now let's do something in practice with this. Okay, what I want to do now is I want to establish an encrypted connection between my laptop and some other device in my network. I will just use my DNS server for that. So I will open a second terminal here. Okay. The first thing I want to do now is I will create the keys. Okay, so I will create a directory for that. And to create a key, you can run open SSL with the command gen RSA to generate an RSA key. You can set the number of bits for it, like 4096 for example, and then it will write that key to standard out. You could redirect that into a file, or maybe through some SSH connection to some other machine, but I personally like to set the output file to ca.pem, so my very own certificate authority. .pem is a common file extension for private keys. And I will also create one for the laptop and one for the DNS server. Okay. Now the next thing I want to do is I want to sign these keys, but to sign something you need a private key but also a certificate. Okay, and I don't yet have a certificate for anything here. So where do I get this initial certificate? Well, I will self-sign the CA certificate. Okay. Normally when you go to some website and it says, hey, do you want to accept this certificate, because it's self-signed or something, you should not accept self-signed certificates. But the question is, do you trust the person who signed this? Okay. And when that's somewhere out in the internet, well, you don't know who signed that, so you wouldn't trust them. But in this case, we created this so we can trust a certificate that we have signed ourselves, okay, because we trust ourselves. Okay, so how do we sign it? First, we need to generate a certificate signing request. Open SSL rec for request -new -key. Here we pass a private key that we want to sign. OpenSSL will just extract the public key from it and only give that out to the people who are supposed to sign it. Okay, don't worry, you're not breaching your security if you give such a certificate signing request to someone else. Okay. And I will set the output file to ca.csr as in certificate signing request. Now it asks me a few questions, like which country am I in, two-letter code, DE for Deutschland, Germany. Brandenburg, but you don't have to answer these questions. I will just skip some of them. But this organization name, you should really answer this question, because when somebody imports your certificate, then this string will be shown to them. Okay, they will be asked, hey, do you trust this company or this person? Okay, and yeah, if you don't answer this question, then they will be asked, hey, do you trust empty string? And then they should say, no, I don't trust empty string, and refuse to accept your certificate. So I will answer this question. The common name is also an important thing that you must answer, because well, this will be compared to the URL that you're trying to connect to. Okay, if a client tries to connect to your server and the certificate says, hey, this is for dns1.engelmann.local, but you are not trying to connect to dns1.engelmann.local, then your client will say, hey, this doesn't match, I'm not connecting. Okay, so for that reason, I will set this to engelmann.local, because I don't have any server for the CA, right? The CA is not bound to any server in that sense. Okay, this is for my entire network, and that's why I will set this to engelmann.local. No email address. I might set a password here. Okay, a super secure password. And no company name. Okay, and now you see I now have the private key for the CA and this certificate signing request. Now, how does this certificate signing request get answered? How can this be signed now? I mean, there are easier ways for this, but I want to go the extra mile here. So with OpenSSL, we can sign this with the command x509. And this is really what I mean with, with usability. What is this? What am I telling this program? I want to do x509. That's not a command. So we will x509 the request. We will assign the key with our private key. You know, I said the CA uses its private key to sign keys. I will set the validity of the certificate to 365, or let's say 3650 days. Then we pass the certificate signing request as input file, and as the output file we set ca.crt as in certificate. Okay, certificate request self-signature okay, and here are the things that we entered in the in these questions up here. Okay, so now we have a private key, a certificate signing request, and a certificate. We can delete the request now because it's because the key is signed now. But anyways, so now that we have a private key and a certificate for the CA, we can now use these to sign the other keys. We can do that with the same command that we used before. DNS1PEM, DNS1CSR as output file. And if we do that, we will get these same questions again, but if we don't want to answer these questions again and again, we can also pass the parameter subj for subject. And in here we can now set these fields separated by forward slashes. And we could now set C for the country to Deutschland, for example. With O, you can set the this organization name, you know, that I set to Victor Engelmann before. Here I think I will set this to Victor Engelmann also. And the common name again is also very important. So I will set this to the host name of the machine that will use this key, which was dns1.engelmann.local. Okay. So now we have a private key for the DNS server and a certificate signing request. So let's sign this certificate signing request now. Open SSL with the completely self-explanatory command x509. So we will x509 a request using the certificate authority ca.certificate, the private key CA key, which is ca.pem. The input file will be the certificate signing request dns1.csr, and the output file will be dns1.certificate. Okay, and now let's do the same thing again for the laptop. Private key, certificate signing request, and this will be for laptop.engelmann.local because that's my host name. Okay. Now we have a certificate signing request for the laptop, and using our CA, we will sign it. The request and write the certificate. Okay. So now we have 3 files for each of these cases, the CA with a certificate and a private key, and yeah, we don't need the certificate signing requests anymore. Okay, so now we have the private keys and corresponding certificates for the CA and also for both machines. And yeah, now I will copy the CA certificate to the DNS server. Okay. And I will also copy both files for the DNS server. Okay, now the situation that we have now is that both machines have their own private key, their own certificate, right? And both machines have this CA certificate. And these are the 3 ingredients that every machine needs. Okay. So let's try to establish a connection using these things. So here on the DNS server, I have these 3 files now, and I need to install Nmap. Because Nmap contains a program called NCAT, which is very similar to Netcat, but yeah, Netcat doesn't support SSL. NCAT supports SSL, that's why I have installed this now. So on the server I can now run NCAT in listening mode, so I'm running a server. With a DNS1.certificate as certificate file. And the private key as SSL key. And let's run this on port 5000. Okay, here on the Raspberry it is apparently not in the Nmap package. So yeah, whatever. I've installed it now and try again. Okay, now on the client side, I will connect to this with NCAT, with --SSL-verify. So otherwise NCAT will just accept any certificate. Here we now require that NCAT actually verifies the certificate. SSL trust file is the CA certificate, and I try to connect to s1.engelmann.local on port 5000. And this is looking good. So if I write something here now, you see here on the server it has arrived, and if I send an answer now, it has arrived at the client. But to prove that this actually works, let me generate another key. Okay. So now I have an additional CA here. Let's run the server again. If I now connect to the server, but using this other trust file here, the connection is refused because, well, the certificate that the server is using here is just not signed with the trust file that I have here. Okay, so the certificate doesn't match this trust file here. And this is actually what you see in practice. When you run an SSL-enabled program like, let's say, an Apache web server, you will have an option. To set a certificate and a private key. Okay, and yeah, the certificate needs to be signed using some CA. We've seen how we can generate that, and then we just need to tell all the clients to trust that CA so that they will accept these public keys from the servers, okay, that are coming from these certificate files. But of course you don't want to specify this CA certificate every time you connect to something, right? So what you do instead is you take this file and you install that on the machines. Now you should absolutely not install certificates from unknown sources, but here this is a self-signed certificate that we have signed. We can trust it, and then we can install it. And yeah, how do we install that? We install the package ca-certificates. It's already installed. What we can do now is we can install this certificate like this. So here we really only need the public key of the CA, right? The private key of the CA, you don't give that to any of your coworkers, you keep that to yourself. You only give this public key to your coworkers. They only install that, or you install it for them. You copy that to user local share CA certificates. Okay, and after that you run update CA certificates. And now you can connect to the server without specifying that certificate all the time. So let's restart the server one more time. And now we can connect with ncat dns1.engelmann.local 5000. Connection reset by peer, because we still have to tell it to SSL verify. Start the server again. Okay, and now we have a connection without specifying the certificate manually. Okay, so we've now installed it in the certificate vault. But what about this laptop CRT and laptop.pem? The thing is, here we only connected from the laptop to the server, right? And yeah, normally you only need a private key and a certificate in one direction, so that you can have a secure communication between the machines. And the client doesn't really authenticate itself against the server. You know, if you're running something like a web server, it typically doesn't care who is my client. It gets some requests and it answers these requests without caring who is the client. But of course, there are other cases where the client also should authenticate itself against the server. Like, for example, in cloud computing cases, Kubernetes, for example, requires that the clients authenticate themselves with such a private key and a certificate. But yeah, here in this case, we only needed it in one direction, so for this case, we actually didn't need them. Yeah, anyways, that's all I wanted to show you today. If you like this video, like it, share it, subscribe, and yeah, share this video. Everybody needs to know this stuff. This is really way too hard in practice. So yeah, really share it. So yeah, see you next time.